2.2, power functions with modeling. A power function, f of x, can be seen in the form k times x of a. Here in the power function, k is the constant of variation. And we see here that k and a are non-zero constants. So k is the constant of proportion, constant of variation. Okay, here are some equations that we use all the time. We have circumference, and area of a circle, force of gravity, Boyle's law. You can have direct variation and inverse variation. Direct variation is like y equals kx, and inverse variation would look more like y equals k over x. That's usually the form that you will see for direct variation or inverse variation. Example 1. From empirical evidence and the laws of physics, it has been found that the period of time t for the full swing of a pendulum varies as the square root of the pendulum's length, L, provided that the swing is small relative to the length of the pendulum. Express the relationship as a power function. So t is a function of L, time is a function of the length of the pendulum. And I'm going to use this for my L. And let's see, it varies as the square root of the pendulum's length. So it varies. It doesn't say inversely, so you know it's directly. That it directly varies with the square root of the length. And express this relationship as a power function. This is not a power function, but it's very easy to make it a power function. We could say T of L equals K times, change the square root to a fractional exponent. That would be L to the 1/2. Example 2, state the power and the constant of variation for the function, graph it, analyze it. So we have the cube root of x. We could rewrite this as, let's see, y equals x to the 1/3. So there's this part here. We've got this. Now we just need to know what the constant is. What is the constant? That would be 1 times. And if we look at the graph, so for a cube root, all right, so for a cube root, I just need to pick numbers that are going to work out evenly. Like the cube root of 0 is 0. The cube root of 1 times 1 times 1 is 1. So the cube root of 1, when x is 1, we get 1 for an answer. How about the cube root of -1? -1 times -1 times -1 is going to be -1. And so if I have my table of values, x, and we have the cube root of x. 0 is 0, 1 cubed is 1, -1. The cube root of -1 is -1. -1 times -1 times -1, 3 times is still -1. What is another perfect cubed? We could do 2 times 2 is 4 times 2 is 8. So the cube root of 8 would be 2. And the cube root of -8 would be -2. And we can plot those points. So we have -1 is -1, and then 8 is 2, and -8 is -2. And so it looks like this, comes up, and it's changing and going. This is what a cube root looks like. If I turned it sideways, it would look like a negative cubic. When I have it going the right direction, it is a cube root. Okay. Now I can answer the questions. The domain would be from negative infinity to infinity. And it's going out ever so slowly in the range direction. So that would also be from negative infinity to infinity. This is continuous. If I start from the left and I look to see what it's doing, what is it doing? Is it going up? Is it going down? I would say that it's increasing from negative infinity to infinity, and it's not decreasing anywheres. Does this have symmetry? I would say that it has symmetry about the origin. So if I was to rotate it 180 degrees, it better look just like this. Rotate it 180, it looks just like this. It's still increasing. So yes, this has point symmetry. This has point symmetry at the origin. This is not bounded above or below. There are no local extrema, max and mins. It has no asymptotes. And then if we look at the end behavior of each tail, so we would say the limit as x approaches negative infinity of this function. So as x approaches negative infinity, what are the tails doing? They are also heading towards infinity, going out, 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 out. So you would say that this would be negative infinity. And then when you have the limit, you also have to look at the right tail. And so you have the limit as x approaches positive infinity of the function. As x approaches positive infinity, we can see that this tail is going out, 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 which would also be positive infinity. We see here that we have a fraction, so we have an undefined place. There's a vertical asymptote wherever the denominator equals 0. The vertical asymptote is where the denominator equals 0, and that would be at 0. So the vertical asymptote would be x equals 0. The horizontal asymptote, we're looking at the degree of the problem. So we have 1 over x squared. This could be x to the 0 because we're looking at the degree. X to the 0 is 1, and 1 times 1 is still 1. So we see that the degree of the numerator is less than the degree of the denominator. That means that the asymptote will be at y equals 0. Remember, if the degrees were the same, if it was x squared over x squared, you would just peel off the coefficients, and that would be where your asymptote was at. Now, graphing this. All right, x is -2. We have 1/4. When x is -1, we get 1. When x is 0, we don't get anything. It's undefined. When x is 1, we get 1. When x is 2, we get 1/4. -2. -2, 1/4. -1, 1. And so we can see it's bounded by these asymptotes. It rides along the asymptote and rides along this asymptote. It can't cross over, so it's bounded in this region. We now move on to 1, 1, and 2 and a fourth. And again, it would be riding along the asymptote, down and riding along the asymptote. And there is our function. The domain would be, for this, we can see that there's a problem at 0, so we would say it's going from negative infinity to 0, not including 0, so rounded. In union with, it's going from 0 to positive infinity. The range would be going from 0 to positive infinity. We would say that, let's see, this is discontinuous at x equals 0. Discontinuous at x equals 0. Okay, so we can see that it's increasing here. As I go over, it's decreasing. So it's increasing from negative infinity to 0, and then decreasing from 0 to positive infinity. And we can see that there is symmetry about the y-axis. That means even symmetry. So symmetry about the y-axis, therefore even. And this has point symmetry at the origin, therefore odd symmetry. Going back to the previous problem, I forgot to put down if it was even or odd. And for this one, it is, where is it bounded? Is it stopped someplace? It is stopped from going down. So it's bounded below, but not above. And does this have any local max and mins extrema? No. We know that we have our asymptotes are here. And then the end behavior. Let's see, we're looking at, as we're going, x is going to negative infinity. So the limit as x approaches negative infinity of this function equals, well, it's not going to positive or negative infinity. It's heading towards what? The limit then is it's heading towards 0. It's not going to positive infinity or negative infinity. It's riding along this asymptote at 0, so it's approaching 0. We would say that the limit as x approaches positive infinity of this function would also be approaching 0. Example 3, describe how to obtain the graph of the given function from the graph of g of x equals x to the n with the same power n. Sketch the graph by hand and support your answer. So I would start with y equals x cubed. When x is -1, we get -1. When x is 0, we get 0. When x is 1, we get 1. So -1, -1, 0, 0, 1, 1. Maybe we think that's a line. We probably should check maybe -2 and 2. -2 cubed is -8. And 2 cubed is 8. -2, 2, 4, 6, 8. -2 is -8, and 2 is 8. So we can clearly see now that it is not just a straight line. It has 2 turns because it's a cubic. So we're coming up and turn and going up. So you can see how similar x cubed is to the cube root that we just graphed. They're very similar. All right, that's the first one. And then the next one would be to multiply by 2 the x is not being multiplied by 2. Remember, if they wanted the x to be multiplied by 2, it would have to be in parentheses, but that is not what we have here. 2 is being multiplied to the function, and the function is y. So that means that I am going to want to multiply 2 to all my y values. So multiplying 2 to the y values. 0 times 2 is still 0. 1, what is this? This is a 1. So 1, make sure I have my numbers right on my graph. All right, now this is 1. So 1 times 2 is 2. And 8 times 2 would be 16. So we don't need to do that. And again, over here, negative 1 times 2 is negative 2. So it's kind of hard to see on this one. But you do see it stretched a little bit. Being stretched, it was laying out, and now it's being stretched up. So this would be y equals 2x cubed. And this one is y equals x cubed. All right, looking at the next one, we're going to start with y equals x to the 4th. So when x is 1, we get 1. When x is negative 1, we get positive 1. When x is 0, we get 0. When x is positive 1, we get 1. And so we can see this looks a lot like a degree 2. Because it doesn't have x cubed, x squared, x with it, you're not going to see 4 terms. It's going to look more like an x squared. The next thing I'm going to do is do the negative. So again, if it was with the x, it would be on the inside of the parentheses. We're negating the function y. So when you negate y, you're reflecting over the x. So when y is 1, now it's going to be negative 1. 0 will still be 0. And then this one will also be down here at negative 1. The last one that we're going to do is multiplying by 2/3. So again, we're going to be multiplying our y values by 2/3. This is still going to be 0. Negative 1 times 2/3 is negative 2/3. So I need to back this up to 2/3. And that would be true for this side as well. We're still at negative 1, so it's going to be at 2/3. And you can see that multiplying by 2/3 is shrinking. This is shrinking vertically.